Today, my presentation will focus on the separation of mixtures of ethene and ethane using cobalt gallate. The pores of cobalt gallate are such that the ethane is virtually excluded due to diffusional limitations, and the adsorption and diffusion both favor the alkene. And in a paper just online in separation and purification technology, researchers from the Zhejiang University in China have reported the use of cobalt gallate pellets in a vacuum swing adsorption process. And I'm going to discuss some details of their findings. Watch also my previous presentation on alkane-alkene separations with MOFs, metrics for the evaluations of MOFs, and transient breakthrough simulations on my YouTube channel. But let's focus on cobalt gallate pellets in PSA operations. This paper in Separation and Purification Technology 2023 reports transient breakthrough experiments in laboratory scale tubes, and the data is then used to simulate a four-step PSA scheme for separating ethene mixtures using the Aspen software. Let's look at the dimensions of the laboratory scale unit that was reported in this paper. The internal tube diameter is 10 millimeters. The length of the packed section is about 15 millimeters. The voidage of the packed bed that is packed with cobalt gallate pellets is 0.57. The flow rate of the gas mixture entering the tube is 1 milliliters per minute. The superficial gas velocity of the mixture flowing through the tube is calculated to be about 0.2 millimeters per second. The interstitial gas velocity, which is the superficial velocity divided by the bed voidage, is 0.37 millimeters per second. And the contact time between the gas mixture and the pellets can be calculated as simply the length of the packed tube divided by the interstitial gas velocity, and that is 130 seconds. The diffusional time constant for ethene, which is the ratio of the Maxwell-Stefan diffusivity for ethene divided by the square of the radius of the pellet, is 2.9 10⁻⁴ per second from uptake experiments. And therefore, if we multiply the diffusional time constant by the contact time, we get 3.8 times 10⁻². Let's turn to the industrial scale unit that has been simulated in this paper. The column diameter is 0.46 meters. The height of the column is 4.61 meters. That should be compared with 50 millimeters in the laboratory. The voidage of the packed bed, again packed with the same cobalt gallate pellets, is 0.57, identical to the one used in the laboratory scale. The flow rate of the gas mixture entering the fixed bed adsorber is 1.9 cubic meters per minute compared to 1 milliliters per minute in the laboratory scale. The superficial gas velocity of the mixture entering the column is 0.19 meters per second, and the interstitial gas velocity is 0.34 meters per second. We can see that these are significantly higher by about 3 orders of magnitude compared to the laboratory scale unit. The contact time between the pellets and the gas mixture is 13.7 seconds compared to 130 seconds in the laboratory experiments. The diffusional time constant may be the same because it's the same diameter pellet, and the intracrystalline diffusion coefficient, say, is the same. So it is 2.910 minus 4. And therefore, if we multiply the diffusional time constant by the contact time, we get 4 times 10 minus 3 as compared to 3.8 times 10 minus 2. So we should expect diffusional influences to be more severe in the large scale unit as compared to the laboratory scale unit. Indeed, in my presentation titled Ethane separations with cobalt gallate on my YouTube channel, I show with calculations that the simulations for the PSA scheme should be carried out with due care and should incorporate the Maxwell-Stefan diffusional formulation rather than the simplified LDF formulation. This is because diffusional influences are more severe by about a factor of 10 on industrial scale compared to the laboratory scale. This is a message that is not often underscored in the published literature.